Hello class. Today we will be looking at section 4.2 that will cover the binomial distribution. So to start off, suppose an experiment possesses the following properties. 1. There is a fixed number of trials n. 2. Each trial results in one of only two possible outcomes, success and failure. 3. The probability of a success is the same for each trial, meaning it's consistent. 4. The trials are independent of one another. And 5. X equals the number of successes. Such an experiment is called a binomial experiment. Note that several of the properties found in the Bernoulli distribution are also found in the binomial distribution. Let's look at an example. Determine if the following is a binomial experiment. A fair coin is tossed 25 times and the observed number of heads is observed. Well, our first property says that there's a fixed number of trials n. In this case, n equals 25 trials, so that checks out. Property 2. Each trial results in one of only two possible outcomes, success and failure. In this case, success would be heads, failure would be tails. There is no other option. So that looks good. Number 3. The probability of a success is the same for each trial. Well, we know from our previous fair coin examples that P, our probability of success, equals the probability of heads, which is 1/2. So that's good. 4. The trials are independent of one another. Yes, we can confirm that our tosses are independent. And 5. X equals the number of successes, and we've determined X is our number of heads. So the answer is to determine if this is a binomial experiment. The answer is yes, it is. Now, let's look at some more of the theory behind the binomial distribution. So, general binomial distribution. Suppose X counts the number of successes in a binomial experiment consisting of n trials. Oops, that got caught off a little. Then X follows a binomial distribution. Our notation for this would be X, little tilde, bin, in parentheses n, which is our number of trials, comma p, which is our probability of success. Or actually, I should clarify, probability of success for a single trial. A little cautionary tale, and I've already warned you already. Unless n is small, and by that we say n is less than or equal to 5, it is inefficient to use probability trees. Personally, I even consider that to be high. I would say n less than or equal to 3 for a probability tree, but either way, we'll go with what the book says. So instead, we can use the binomial distribution formula to calculate binomial problems. The following is the formula for our binomial distribution. P of x equals n choose x times p to the x times 1 minus p to the n minus x for x equal to 0, 1, 2, ... all the way to n for our n trials. To break that down, know that P of x stands for the theoretical probability of x successes in n trials. And if you think back to our combination section, n choose x equals n factorial over x factorial times n minus x factorial. And it tells us the number of different ways we can obtain x successes in our n trials. Lowercase p is the probability of success on a single trial. So from our coin example, p would equal 0.5 for our x equal to 0, 1, 2, ... all the way to n. This means we can use this formula for each of the values of x. So let's do a practice problem, calculating the binomial probabilities. First example, a couple plans to have 2 children. Arbitrarily, let's label male as a success. Then P equals the probability of success, and we'll assume that to be 50%. And recall, this is a binomial distribution. So for A, find the probability that the couple has no male children. This means X would equal 0. Using our binomial formula, P of 0 equals 2, choose 0, times our P, 0.5 raised to the 0, which is X, times 1 minus 0.5 to the 2 minus 0. From here, we are just going to calculate and simplify until we get our probability of 0 to equal 0.025, or 25%. Part B asks us to find the probability that the couple has 1 male child, where X equals 1. Well, P of 1, we let X equal 1. We know our P equals 0.5. Plug in and solve. P of 1 equals 2, choose 1, times 0.5 to the first, times 1 minus 0.5 to the 2 minus 1. If we plug in and simplify, well, we've already plugged in, but if we simplify from here, we will have that P of 1 equals 0.5, or 50%. Part C asks us to find the probability that the couple has 2 male children. So that would be X equals 2. So the P of 2 equals 2, choose 2, times 0.5 to the second, times 1 minus 0.5 to the 2 minus 2, which we know to be 0. Simplify, P of 2 is going to equal 0.25, or 25%. Notice, if we were to list out our sample space for having 2 children, you're either going to have boy, 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 girl, girl, boy, or girl, girl. Or I guess, sorry, we should have used male and female, but you get the idea. We had a sample space of 4, and we established that having 2 boys and 2 girls each had a 25% chance of happening, or 0.25, and having 1 of each would be 0.50. We add that up, we have our probability of our sample space to equal 1. So that looks good, and it's a good review of something we've already learned. All right, next up, the binomial probabilities using tables. So table 1 in your textbook gives the cumulative binomial probabilities for certain values of n and p, such that p of x is less than r. This is very important to remember, that it is x less than or equal to r. So for example, if we want to find the probability of x less than or equal to 8 for n equals to 20 and p equals 0.3, using the table, we would establish that the probability of x less than or equal to 8 equals 0.8867. Using another example, with n equal to 10 and p equal to 0.4, we would establish that the probability of x less than or equal to 5 equals 0.8338. This is just a faster way of using our binomial formula, because what does, say, the probability of x less than or equal to 7 really mean? What it really is it's the probability of x equal to 0, or x equals 1, or x equals 2, all the way to x equals 7, which is really saying that the probability of x less than or equal to 7 is the probability of x equals 0 plus the probability of x equals 1 plus the probability of x equals 2 plus ... all the way to plus the probability of x equals 7 by our special addition rule. So we can do our binomial formula for, say, in this case, it would be the summation is I equals 0 to 7 of n choose x for p to the x times 1 minus p to the x for whatever our p and n are. We can solve this and get the probabilities. That can take a while by hand, which is why we have the cumulative binomial probability table. But if you prefer to work things out by hand, or you don't like using the table for whatever reason, this is an alternative way to go. Yeah, oops. No, looking at this, I realized I made a slide. No, it looks good. Thought I made a mistake, but we're looking good. All right, so we can use the cumulative binomial table 1 to find simple binomial problems. Example, the probability of x equals 6 equals the probability of x less than or equal to 6 minus the probability of x less than or equal to 5. How does this work? Well, the probability of x less than or equal to 6 minus probability of x equals less than or equal to 5. We can expand that out. So probability of x less than or equal to 6 is the probability of x equals 0 plus probability of x equals 1 plus probability of x equals 2 plus probability of x equals 3 plus the probability of x equals 4 plus the probability of x equals 5 plus the probability of x equals 6. Subtract the probability of x less than or equal to 5, which is probability of x equal to 0 plus the probability of x equals 1 plus the probability of x equals 2 plus the probability of x equals 3 plus the probability of x equals 4 plus the probability of x equals 5. By removing our square brackets and combining similar terms, we are just left with the probability of x equals to 6. To be perfectly honest, I would never do this. If I'm just asked to find the probability of x equals to 6, I would definitely use the probability formula. I think that would be a lot faster personally, but that's a personal preference. You can do whichever makes you feel most comfortable. I don't know why I'm trying to erase this. I think we've all established that this does not erase well. All right, let's take a look at another example of this. So for example, let n equal 10 and p equals 0.5, the probability of x equals 6 equals the probabilities we've established of x less than or equal to 6 minus the probability of x less than or equal to 5. Using the table, the probability of x less than or equal to 6 is 0.8281 minus the probability of x less than or equal to 5, which is 0.6230. Subtract, and we will get 0.2051. This next example is very interesting, and it's definitely, you need to remember what you're looking at when you're using that table. So if we let n equal to 20 and p equal to 0.4, if we want to try to figure out the probability of x is greater than 10, well, our table gives us the probability of x less than or equal to r. So using our complementary rule, we can flip that around and say that the probability of x greater than 10 is equivalent to 1 minus the probability of x less than or equal to 10. And then from there, we can use our table 1 minus 0.87525, which equals the probability of x greater than 10 to be 0.1275. And in here, this just kind of goes into what I've already said. Now, the previous example used the idea of complementary events. We know that the probability of event equals 1 minus the probability of not the event. So for x greater than 10, we know that's 11, 12, 13, comma, dot, 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 all the way to 20. And not our event, which is x is less than or equal to 10, would be 0, 1, 2, dot, 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 all the way to 10. You know, it's your call to use, when it's appropriate, to use the complementary event. Sometimes, if this was x, so you're saying our sample space was still n equals to 20, and we want to know what is the probability of x is greater than 18. I probably would not necessarily use the complementary rule in this case. I might just find the probability of x equals to 10 plus the probability of x equals to 20 and solve it that way. Again, personal preference. It all depends on what you're given and how you're solving. So similarly, for our next example, we can still use that idea of the complementary. So if we let our sample size equal 10 and our probability of success be 0.3, if we are trying to find the probability of x is greater than 2, we know that's the same thing as asking for our discrete cases. It's the same thing as asking the probability of x is greater than 1, which then by the complement rule is 1 minus the probability of x less than or equal to 1. Using our table, 1 minus 0.1493, which equals, 0.8507. And there are some other examples if you need some practice or some help in section 4.2. The last two slides of this section focus on how to find the mean and the standard deviation. You should definitely be able to see the relationship between the Bernoulli experiment and the binomial experiment by looking at their mean and their standard deviation. So for our binomial distribution, our mean is equal to n times p. So our number of trials times our probability of success. The standard deviation is equal to the square root of n times p times 1 minus p. It's not given here, but we can already go ahead and we know that our variance, or sigma squared, is going to just be equal to n times p times 1 minus p. Using this in an example, a couple has 2 children. Our n is 2. Our probability of success is 0.5. So that means our mean, n times p, is going to be 2 times 0.5, which is going to equal 1. I.e., that means that the mean number of males in a family of 2 children is 1. To calculate our standard deviation, again, sometimes we call this the standard error, it is equal to the square root of n times p times 1 minus p, plugging in with what we know. Our sample size is of 2, p is 0.5, 1 minus p would be 1 minus 0.5. Simplify, and we would get a standard deviation of approximately 0.7. And a note, if the value of p is unknown, we can estimate p by using a sample proportion of success with p hat equal to x over n. X is our number of successes and n is our number of trials. Let me remind you guys that usually we don't know what the true population mean and population variance standard deviation. Usually we do have to use the sample size. So using that p hat is not uncommon. All right, guys, that is the end of the binomial distribution lecture. You guys will get to listen to me again when I talk about the Poisson distribution. Have a good night.